The human eye is a highly evolved, variable focus optical system. It captures light rays from a three-dimensional environment, mapping them onto a fixed, two-dimensional plane. The process begins at the cornea. This transparent outer layer performs roughly 65 to 75% of the eye's total static refraction. This high degree of bending is a result of the density differential between the outside air and the tough, fluid-filled tissue of the cornea. The crystalline lens serves as the second stage of the optical system. It fine-tunes the focal point, ensuring incoming rays converge into a sharp image on the retina. Ring-shaped ciliary muscles and suspensory ligaments hold the lens in place, providing necessary mechanical support. The eye functions as a biological refraction engine, utilizing these distinct material boundaries to bend incoming photons into a coherent signal. This system operates under a rigid constraint. The physical distance from the lens to the retina is completely fixed. Because the image distance cannot change, the focal length of the lens must physically alter to keep objects of varying distances in focus. To focus on a near object, the ciliary muscles contract. This allows the elastic lens to bulge and thicken, increasing its converging power. For distant objects, the ciliary muscles relax. This pulls the lens flat, decreasing its converging power to align with parallel light rays. These mechanics define the system's operational limits, a near point at approximately 25 centimeters and a far point at infinity. Accommodation is the continuous physical deformation of living proteins required to solve a mathematical problem of focal distance. Refractive errors are structural failures where the eyeball length and lens curvature fail to geometrically align. Myopia occurs when the eyeball elongates along the visual axis. Light rays overconverge in front of the retina. Because they cross too early, they diverge, creating a blurred spread of light instead of a sharp point. Hypermetropia is the inverse structural flaw, a shortened eyeball or an insufficiently curved lens. The converging rays hit the retina before they can meet, pushing the theoretical focal point behind the eye. The eye lacks the converging power necessary to resolve near objects, which remain blurred and out of focus. Vision defects are architectural failures, an inability to match the receiver plane to the eye's refractive power. Correcting these spatial mismatches require altering the angle of light rays before they reach the cornea. A divergent concave lens corrects myopia by spreading incoming rays outward, shifting the internal focal point back onto the retina. For hypermetropia, a converging convex lens pre-bends light inward, pulling the focal point forward onto the retinal wall. Optical correction is a quantifiable equation. Using the formula power equals 100 divided by focal length, doctors can calculate the precise dioptric power needed. Clinicians map these geometric failures using specialized diagnostic optics to determine the exact correction. Age introduces further mechanical degradation. Presbyopia, the loss of lens elasticity, often requires split lens corrections, like the bifocal logic seen in these early spectacles. The entire history of optometry is the practice of using manufactured geometry to restore the biological limits of the eye. Before light reaches the cornea, the atmosphere filters and splits the incoming signal. In dispersion, a material's refractive index changes based on the wavelength of the light passing through it. Shorter wavelengths interact more strongly with the medium and are slowed down, causing them to bend further than longer wavelengths. A geometric prism demonstrates this clearly. White light splits into its component spectrum as violet bends the most and red bends the least. Analyzing these angles of deviation requires precise instrumentation, such as this antique spectrometer, to map the optical properties of different media. This same logic applies to spherical raindrops suspended in the atmosphere. Sunlight entering a raindrop refracts and splits into colors. Hitting the back of the droplet beyond the critical angle causes total internal reflection. Exiting, the light refracts again, emerging at highly specific angles, 42 degrees for red, 40 degrees for violet. A rainbow is a geometric optical phenomenon, requiring millions of droplets perfectly aligned with the observer's vantage point. Rayleigh scattering violently redirects light upon impact with microscopic atmospheric molecules. This behavior is governed by a mathematical law. Scattering intensity is inversely proportional to the fourth power of the wavelength. Consequently, the atmosphere continuously scatters high-frequency blue light in all directions, giving the daytime sky its bright, characteristic blue color. At sunset, when the sun is low on the horizon, sunlight must travel through a much thicker section of the atmosphere. This extended path scatters away the blue wavelengths, leaving only the longer red and orange wavelengths to complete the journey to the observer. These red photons pass through the cornea, accommodate via the lens, and strike the photoreceptor cones. Human vision is a continuous chain of physical optics, linking our biological anatomy to the physics of the universe.